So we're going to go all the way back to Tuesday and talk about the first way we learn to divide these things, okay? So when we talk dividing polynomials, so you got to think what we're doing here. We got x to the third plus 3x squared minus 4x minus 12, and I want to figure out, I want to divide that by x minus 2, and I want to figure out what the answer is. We did this thing with numbers, like 10 over 3. We want to know the answer. That's something we've done forever. We're essentially doing the same thing, and even though we don't review it, if you had searched other videos on your own, you might come across them doing this with what's called long division. You guys remember long division? It's just another scaffolding to do division, okay? Synthetic division, this area model division or box division, and long division all accomplish the same thing. It's just, it looks different. Numbers go into a different spot, okay? We don't review long division because I think it's a little bit tougher and it's technically not in our standards. Box is usually a little bit easier because working backwards in this to divide tends to make more sense because we've used this to multiply almost probably since the very beginning when you first learned to multiply two binomials together. So we're very accustomed to, well, I know if I know the number in here, I know that the two sides of that box were multiplied together to give me that answer, and I can work backwards, okay? You don't usually write long division out much anymore, which is why we kind of ignore it. But if you do see it in there, understand that it is the same thing as the box. If you want, I'll gladly show any of you how to do it. It's not that tough. I believe if you go to my YouTube channel, I sent you a link for it. There should be a video because we do review it in pre-calculus just so we've seen it. So, you know, if you are curious about it, it wouldn't necessarily be something you're tested on, but if you want to know what's going on with that, feel free to watch that video and, you know, explore on your own and ask me questions. But anyways, we want to do this, and the idea here is that the way that this works is dividing can be tough, but we want to think of the division as we're going to do algebra with it. Whatever this missing part is times x minus 2 is how I find the answer when I multiply those together. That's the answer that I get here. So if we use this idea to set up our box, that's why this number goes on the bottom. Because if you knew both of these sides, you would multiply this out. The front number would be over here by itself. The diagonals would add up to the numbers on the bottom. Remember this setup, and then that last number should be by itself. It works the same way. But we don't know the two sides this time, and we're not trying to find the answer at the bottom. We know the answer at the bottom, and we know one side is x minus 2, and what we're doing is we're working backwards to this. I want to figure out what this other side is. This is the question mark in that setup. I want to figure out what has to be up here to make this work. And because we know how to multiply with this, we can work our way backwards. So the key to getting this to work is we're going to work in each column and end up filling in each column one at a time. And we always end up starting in the middle. So we know that this number right here, this x to the third, was by itself in this top box. And what that's going to allow me to do is, well, I know that this x times whatever is missing up here has to give me x to the third. So this should have a 1 in front of it, right? So should this. So 1 times something equals 1 means that this coefficient should be a 1. This is x to the first. I need x to the third in here. So x to the first times how many more x's will give you x to the third? 2 of them, which is why this one has to be x squared. X squared times x will give you x to the third. So we use the middle row to find the top number, the top row. Now that we know the top, we use that to find this bottom number. Because the bottom number can be found just like we would do if we were multiplying. 1x squared times negative 2. That's negative 2x squared. Because this box is found by this number and this number. So that's how we would fill a column. When we go to the middle, we find the top, and then we use the top to find the bottom. Now this is where we need to use the diagonals. I know, because I know the answer, that this value that I found here in the bottom left hand, and it's connected diagonal, these two should add up to positive 3x squared. So what that tells me is this has to have an x squared, because it has to have the same variable to add. And then I only need to worry about the number. Something plus negative 2 is positive 3. That has to be 5. Because 5 plus negative 2 gives you positive 3. So you could even write them off to the side. So 5, before we knew it was a 5, we had it as a question mark. Something plus negative 2 equals 3, and you can use algebra to solve that off to the side each and every time. Well, that means that this has to be 5, so this one is 5. Now that I know the middle, I can work this column and fill this in, just like I did up here. So now I know this number has to be 5x squared. Since I know the outside edge of this, I can use that to find the top. 1 times something equals 5. That has to be 5. This has an x to the first, but I need x squared, so I need one more x right here. Now that I know the top, I use the top and this outside bottom to find this number. 5 times negative 2 is negative 10, and it gets that x to the first with it. And we don't normally write it in the answer, but that is x to the first. I just like to keep them in there because then it gets so I can count the exponents as I do this process. It's one less thing to trip me up as I go through. Then we do the same thing like we did right here. I'm going to erase this one then. Something plus negative 10 is negative 4. So to get that 10 to the other side, we would add it, right? So that means that that has to be 6. It's got to have the same variable. And now that we know the middle, we can find the top and we can find the bottom. So 1 times something equals 6 means that has to be 6. X to the first, and this one is x to the first. Do I need any more x's? Nope, so that's just the number 6. And this one was positive, and so was this one. I should have been putting those in there each time. So now I'll use that to find the bottom. Positive 6 times negative 2 is negative 12. Now this is the part that we leave out when we find this, because you got to think with when you divide, like when we do 10 divided by 3, sometimes you get a remainder, right? Well, technically we always get a number for the remainder. When we do this with box division, we kind of lose this. But what happens is this isn't necessarily always going to be a perfect box. There is a column here, a diagonal there that needs to add up to negative 12. So there's an extra box on this. And that extra box is where the remainder is. But what happens is when we first start this, most of the time, negative 12 plus something is negative 12. This is 0 for this one. We tend to ignore it because, well, it's 0. It doesn't do anything. But technically, this still does have a remainder. If you ask for the remainder of this, the remainder is 0. And actually finding that remainder is one of our goals, because finding this remainder of 0 tells us something special about this polynomial, okay? So I would suggest anytime you do this, even if it's 0, to put it in there. So if you'd looked at the exit ticket yesterday, asked for remainders, didn't it? Asked for a bunch of the remainders, and a lot of them were 0, okay? So just put that in addition. I sent out a polynomial video in the morning yesterday, trying to catch you guys before you got too far into it. I hope you took the few minutes to watch it. But it kind of went over this process. If you make this look like this every time, it will be helpful. So what that means, though, what's our answer? Our answer is up here. So the answer to this division is x squared plus 5x plus 6. That's what happens when we divide these things. There's no remainder, nothing else to worry about. But down here is where this actually becomes more important in our process. What that means is that our big polynomial can be found by taking x squared plus 5x plus 6 and multiplying it by that x minus 2. That's what I just did right here. If I look at this the other way, I know that x minus 2 times x squared plus 5x plus 6 is going to give me the bigger polynomial. And our ultimate goal is I want to take this polynomial and factor it down so it's just linear factors. But what I have now is I have a quadratic. Can I factor that quadratic? Do I need to do division or anything else to factor quadratics, or do we know how to factor quadratics? This is one where we could draw the box that we've always learned and factor this thing out. Factors of 6 that add together to 5 are 2 and 3. It'd be x squared plus 2x plus 3x plus 6. So this is x plus 2 and x plus 3, meaning that the bigger polynomial is actually these 3 roots multiplied together. Which also means, think back to what we did on Monday. It means that those are the x-intercepts. I get an idea of what this graph looks like. I can find its x-intercepts. Factoring these polynomials is actually our ultimate goal. What we just did right here, getting this to this, is what we want to do. In polynomial division, especially when we find a remainder of 0 that proves it's a factor, aids us in that process because we can use the result, and a lot of times we get quadratics and things like that we don't need to worry about division anymore. We can start doing our old methods of factoring these things to find out where it crosses to write its factored form. Now that also takes us into one of these theorems. So we said remainder of 0 means a factor, and we kind of know why that makes sense. What is 9 divided by 3? That's 3, right? And we would say that works out because 3 is a factor of 9, right? Because it gives us a remainder of 0. We say the same thing with polynomials. When we get that remainder, it means that thing goes in evenly and it is a factor of it. And when we start hunting factors for polynomials, they look different. They're not just numbers. They're actually these binomials, these linear coefficients. And then we can use that idea to find x-intercepts and all this other information about our polynomials as we work through. And eventually what we'll learn at the end of the day today is that we can do this with much bigger stuff and not be given a number to start with. We can get a list and actually choose numbers to start with to help us there. But there's also an easier way than division to prove that something is a factor or not. And it's called the factor theorem. So what this says if you have a polynomial, let's say that this right here, what we were given was our p of x. And we want to know if this x minus a is a factor of this thing. The only way that works is if I plug the number a in to this polynomial and get an answer of 0, meaning that it's going to be the same thing as this remainder that I find here. So if this is x minus a, let's practice this. If x minus 2 is what my x minus a is, what would a be for me to plug into this one? Now what we get tricked with is that minus is already written in there. The easiest way to make sure you don't make a mistake with this, when you're given this, you're really looking for the 0, not the factor. So set it equal to 0 and solve it. The 2 is what we want to plug in. Remember those signs we're switching when we did roots and factors? So we really want to plug in the 2. So what this says is let's plug in 2. We know that it's a factor because we just did the division. So what it says is if we plug in the number 2 into this expression, we should get 0. So let's actually substitute in 2. I lost my powers, sorry. I want to actually do this math. So 2 to the third is 8, right? 2 squared is 4. Negative 8. And 12. And then if I add all these up, 8 minus 8, 12 minus 12, I get 0. So I plugged in the a value and I got 0. What this tells me, though, is it tells me that 2 is going to be a factor of this polynomial. Now, in isolation, this doesn't seem like it's much helpful. I could just do the division if I wanted to know that. But if I had just given you the big polynomial, x to the third plus 3x squared minus 4x minus 12, and I said factor that down to these 3 parts, and you didn't have any numbers to start with, and you just had to pick numbers and guess, what do you think your chances of finding one of these 3 numbers are? Not without some tools to get an idea of what to look for. But what this does is we could always plug this into our calculator and look at the table. And we can look for when our output is 0, so we know what numbers to start with for our division. Okay? It gives us a quicker way, because look at the amount of math this took versus the, let's say the amount of space this took versus the amount of space this took. Eventually, I am going to have to do this, but I don't want to do this 5 times and not have it work when my goal is to find factors. If I know it's going to be a factor when I start, it makes the process a lot quicker and a lot more straightforward, okay? So that's the importance of this theorem, is eventually I'm going to give you a big polynomial and I'm going to say factor this. Well, we're going to need tools to pick numbers, because you don't want to take Vegas odds on just guessing numbers and hoping you get them right. There's a reason why Vegas builds billion-dollar casinos, okay? Because when you're just guessing, you're going to make a lot of errors before you get it correct, okay? So what we're working through is we're getting some tools to help us make better choices about what we do choose to divide, so that we don't have to take 2 pages to factor each one. Getting a little bit more sophisticated with it, okay? Let's practice another division. Let's do this one, because there's some stuff in here that I saw when I graded this work that I wanted to make sure everybody saw. So let's set this up. So remember, this is the answer. It goes at the bottom, right? This goes on the right side. How big should I draw the box, though? That's the biggest question, right? That's the toughest one. What you've got to remember, the box needs every power of x. This is missing something. What's it missing? It's got an x to the third. It's got an x squared. What doesn't it have? It doesn't have an x. To be able to do this, any sort of division with this, I've got to put that 0 back in. And it kind of works the same way with numbers, right? If I was going to ask you to divide 10,000 by 5, you could look at the front numbers, but then you'd have to add those zeros back into your answer, because even though they don't change the math and you can almost ignore them, they still have place value. Okay, when we're adding and subtracting, this is where mathematicians get lazy and we leave stuff out, so it's less to write, but we've got to put it back in to do the math. So our box for this one look like this. Because we have 2, we're going to have 1 dangle off the front, because remember that first number is always by itself in that column, so it kind of hangs off the front. And then our diagonals will add up here. This should have our x squared in it. And the second one should have our x's in it. And then the process for this is exactly the same as what I just did. So this 2x to the third, let's write it in a different color, jumps up here. And remember, the actual answer we're seeking is going to be written up here this time, not down at the bottom like we were used to when we were multiplying, because we're working backwards. So I like to put the ones and the 1 on this just so I can see them. Because I'm never going to, oh, you didn't put the 1 on the 1, it's wrong or something like that. But if it's something you're having trouble keeping track of the powers of x and stuff like that, do add it in. So 1 times something gives you 2. That's got to be 2. We need x to the third. This is x to the first. So it means we need 2 more up there. Then we come down to our bottom number. And that's going to be our 2x squared times our -3. So that's -6x squared. And once I put x squared in this diagonal, I know that one's got to be x squared. This should go down by 1 factor of x, 1 degree of x every single time. The first diagonal had x to the third. The next one has x squared. This one should both have x in it. This one shouldn't have anything. You can almost fill those in before you work with this and just work with the numbers. So let's keep on moving. So we got to figure the number that goes here. -6 plus something equals +4. That's +10. So that means 1 times something equals 10. This is 10. We need x to the first. Let me get my colors right. This is 10x to the first. Then we use that to multiply to the bottom. 10 times -3 is -30. So -30 plus something gives us 0. So that means this has to be +30. And now we use that to find our top number. So 1 times something equals 30 makes this 30. And we don't need an x because this was x to the first already. And that's all we need. We have it on the left side. So now we can fill in the bottom. 30 times -3 is -90. And this one's pretty apparent, right? There's a problem here. Is this working out for us? And this is where that extra box is critical, because this one does not divide in evenly. It has a remainder. So it means if we were asked the question, is x minus 3 a factor of 2x to the third plus 4x squared plus 5, right now we could say no, because, hey, this number didn't match. It's going to have a remainder. That means it's not a factor. But now we need to figure out what number this needs to be to make this addition work. -90 plus something needs to give us +5. So let's actually list that out. So -90 plus something equals 5. And just treat this like the question mark is a variable. Add the 90 to the other side. It tells us that has to be +95. Now that works, okay? Because really that extra box is just there to make the last diagonal balance if needed. Over here we got 0 because it worked out. It's not always going to be the same number when we get done. That only happens if we get a factor. So here we actually had to put a value there to make this division balance out. We actually have a remainder. So let's talk about how to write that answer. So that means 2x to the third plus 4x squared plus 5 divided by x minus 3. It is equal to something, but we have to deal with this remainder. So we're going to start with the top. It's 2x squared plus 10x plus 30. But now we need to deal with, how do we deal with the remainder? And this is where it's helpful to look back at this division. 10 divided by 3. So 10 divided by 3 is 3 with a remainder of what? Remainder of 1, right? Now, when you write this now, do you go 10, remainder 1? No. What do we do? It's 10 and what? It's 10, and if you did this division in your calculator, you get that 0.3 forever, right? But we know 0.3 is 1/3. Now what we missed with this is a mixed number, which you learned probably, what is this, 4th, 5th grade maybe? If we said this out loud, this is 3 and 1/3. There's actually an operation between these two numbers. It's what made dealing with them mathematically tough. What is 4 and 5? 4 and 5 is 9, right? The word and means plus. So there's mathematicians leaving stuff out again. Mixed numbers have always had a plus symbol in there, but because we use them so commonly and we expect you to know that, we don't ever write it in there. We're going to treat this fraction one, I'm sorry, this polynomial division the same way. We need to write this remainder the same way. So we're going to put a plus symbol over here, and it's going to be a fraction. The top part of it comes from the remainder itself. So the top part is going to be that positive 95. Where did the 3 come from in this original division? The 3 came from our divisor. So what are we dividing by up here? We're dividing by x minus 3. And on something completely additional that you would never have to talk about, well, not necessarily not talk about, but have to actually find. You remember when we found features of rational functions, and some of those horizontal asymptotes became slant or polynomial when the degree of the top was bigger than the bottom? Think about this like a rational function. The degree of the top is bigger than the bottom. That told us that its horizontal asymptote was slant. The equation, slant or polynomial. The equation that that graph has as an asymptote is that. You have to use polynomial division to find out what the actual equation of the asymptote would be. The rest of the rational function is over here. Okay, that's also why when we did that, I said, hey, you're just writing slant or polynomial, because you didn't know how to do polynomial division, so you couldn't find its equation easily at that point. I won't ask you to find them, don't worry, but it's knowledge that you should kind of keep with you. Polynomial division, when you don't get factors, it actually tells you the rational function and it gives you its horizontal asymptote right here. Just a little added thing since we're actually seeing them, okay? All right, let's talk remainder factor theorem again. So we're going to talk about the remainder theorem. So full disclosure, the remainder theorem and the factor theorem are the same thing. Why did we call this one the factor theorem? Because we found a 0 when it came out, right? But overall, this number right here is the remainder. It's the remainder I'm going to find. I get a remainder of 0. What happens with these ones that aren't factors? If we do the same process and we plug the numbers in, we're actually going to see what the remainder would be from the division. So this A is positive 3. So I'm going to plug that in to this expression. 2 times 3 to the third plus 4 times 3 squared plus 5. So this is 2 times 27, 4 times 9 plus 5, right? I'm doing this without a calculator. You guys got to double check me. This is 54 plus 36 plus 5. What happens when you add those three numbers together? What do you get? 54 and 36 is 90. Plus 5, you get a positive 95. What do we see? This positive 95 is the same thing that we got right there. Really, the remainder and the factor theorem, they state the same thing. Plug in the A value from what you want to divide by, and it only works if you have an X minus something, a binomial. If you plug in this A value, you're going to find the remainder every time. But what's important with it is if the remainder is 0, that makes it a factor, and that's going to make it one that we want to research further, okay? So really, we could take Y values, take these A values and plug them in and try to hunt down roots that way, figure out which divisions to start with so we can factor our polynomials. That's the idea. Any questions before I go on to the next thing? Feel a little bit better about it? A little bit? Guys, the factor remainder theorems are kind of a corollary, meaning that this whole idea of finding factors is what we're hunting for, and we're developing more tools to help us in that process to make it so that we can do this quicker and more accurately without as much work, okay? And that's actually where our second method of division works. I'm going to talk about synthetic division. All right, this is a shorthand method for dividing polynomials because this process, while it's not extremely long, is still, if you had to do this 4 or 5 times for one problem, it would take up a lot of space on your paper. These right here are going to be much shorter and much smaller. And because we're only going to work with the coefficients, all we're ever going to do is add or subtract. And it's actually going to work out much quicker. We're going to be doing the same thing that we're doing here. But what we're going to end up doing is we're going to ignore the x and its power, because we're going to use the fact that, hey, the diagonals add up and stuff. We're just going to make it look different. We're going to do that part without the powers. So this is the method for this. And the important thing to remember here is we're still dividing polynomials. I could divide one with synthetic division, and I could divide one with box division, and I would get the same answer every time, okay? So this is a shorthand. Now, this says this will only work if you were dividing by a linear factor with the coefficients of 1 with x. Now, I have an exception with that, okay? There's something you can do to the answer to make it so you can do ones that don't have 1 in front of the x, but we'll talk about that after we get through the basic ones, okay? So steps. I want to divide this polynomial. Now, let's divide it with the box real fast first, so we know what the answer is, because I want to prove to you that we get the same thing. So we're going to take x minus 1 over here, and we're going to put x squared minus 3x plus 2. So this is x squared, which makes that x. Negative 1, negative 2 makes that negative 2. 2, there's no remainder. So that means when I divide it, I should see, as a result, x minus 2. That's my box division, okay? This is also factorable because it's just a quadratic. So I think you're pretty comfortable with the fact that you should get x minus 2 because it's what's paired with x minus 1. The reason I picked one that was simpler to start with is I want to show you that this shorthand is going to give us the same answer so that we have a little bit more faith with it as we work to ones that we don't know the answer quite as readily for. So the steps with this. You're going to write the coefficients of p of x. P of x is your polynomial that you want to divide in the top row. So the coefficients are 1, negative 3, and 2. We're just looking at the numbers. So we just write all the numbers in the top. This has a 1 in front of it. Don't forget about things that have 1s. Don't forget about missing terms that might have 0 as well. So we have an x squared and x and just a constant. So we've got everything. 1, negative 3, 2. Write the value of a to the left. Now here we get back to that a, the same one that we were using for the factor theorem and the remainder theorem. So remember, this is our x minus a. The easiest way to do is to take your binomial, set it equal to 0, and figure out what x should be. For single numbers, that's really easy to do. But it's imperative because since you're going to be working with just the numbers, getting those numbers written down correctly to start is an absolute must, because you won't have anything to kind of check your understanding of it as you go through. So that means this number right here should be 1. Now, we're actually going to divide, but it's going to look really different. You're going to bring down the first coefficient. That's why I have this arrow drawn here. So we bring down the 1. Let me pick a different color. That's like our first column. Now what I need to do is I need to work over and do this process. So the next step is going to be multiply this number that we just brought down by A, your A is up here, and place the results over here. So 1 times 1 is 1. So this number comes from multiplying these two. Then add. So that means I'm going to add these two numbers together. It's always add. -3 plus 1 is -2. And then I'm going to repeat this process until I get to the end, until I run out of numbers. So now -2 times +1 is -2. 2 plus -2 is 0. And I'm out of numbers, so that means that division is done. Now here's the thing with using the shorthand though. So what's the answer? All I got is a bunch of numbers written there, right? So the way that you decipher this, because what we've done is we've taken away all the context of the variable, all the x cubes, x squareds, and everything else. We've got to put them back in. I like to draw a little box on this edge because that's kind of my extra box. This is my remainder. And then if I want to put x back in, I start with x to the 0, x to the first, and then however many numbers, I just count that sequence up one. Meaning if there was, don't write this in here, if there was a 5 right here, it would get an x squared with it. If there was another number to the left of that one, it would get an x to the third. However many numbers you have, how many powers of x is it? So then we combine these things. So our answer is 1 times x to the first, which is x, -2 times x to the 0. This is one that'll catch people. What is anything to the power of 0? It's 1. So this is -2 times 1. You're basically multiplying these things. -2 times 1 is -2. That, because there's no remainder, is the answer. Look. That's exactly what we knew it should have been when we did it with the box. With some of these simpler ones, it's not quite as helpful, okay? But when we get to these longer ones that are more difficult, or especially when we need to do this repeatedly, this is a much faster process than drawing the box. And our ultimate goal is going to be to factor polynomials, meaning we want to get down to this 0 over here and then work with what's left every single time, okay? So let's try another one. I want you guys to do this one first. What's about this one? Anybody catch it? What's this missing? It's missing the x squared. Anybody put it in? And this is where you have to be super cautious using synthetic division. When you draw your box, you'll get an x squared, but you'll have an x underneath it, and you'll be like, hey, that doesn't work. I can see that. Okay, I see, I missed it. But when you use synthetic division, you take those away, there's nothing to tell you. It's just a number, and it just works, okay? So always make sure you look at your polynomial. 2 things you always got to look before you divide your polynomials. Are they in order? And is every power of x represented from the leading coefficient? Meaning, I need x to the third plus 0x plus 1x minus 10. Might not even be a bad idea to write those ones in there just to visualize that they're there. So when we go, this is our x minus a. So our a here is going to be positive 2. So this is going to be 2, 1, 0, 1, and -10. Because by taking the powers of x away with this division, you lose your checks and balances to make sure you've got every piece in there. Okay, so you got to do it first. Pull the first number down, multiply, then add, multiply, write it here, add, 5 times 2 is 10, add, 0. Is it a factor? Yes, this one is a factor. And that's something as we do these divisions and we work through that we want to answer every time, even if it doesn't really ask. This is a factor because it has a remainder of 0. So now let's write our answer out for this. So this is x to the 0, this is x to the first, this is x squared. So our answer from this division is going to be x squared plus 2x plus 5. Now, let's think about this. What that also means is, if our goal is to factor polynomials, we know that x to the third plus x minus 10 is x minus 2 times x squared plus 2x plus 5. Think back to the box. I did the box division here and just made it look shorter. So that still means that this divisor and the result multiply together to give me, now I have a quadratic that I can factor, maybe, to find all the zeros. This one doesn't factor nicely though, does it? Because I didn't set it up to factor nicely. It was more about the missing part than that. But you could still try to factor this. When you get one that doesn't factor with the box, you may need to use quadratic formula to find its zeros. That x equals negative b plus or minus the square root of b squared minus 4ac over 2a. I'm sure I brought back many nightmares from math too. Okay, we won't go into it on that one, but what I'm getting at is we're still overall guiding to the same process of factoring polynomials using this division. Okay, let's practice two more and determine if they're factors. Let's do them together. I think we've got this pretty wrapped up. So this tells me that a here needs to be -1. Coefficients, so check them. Are they in order? And you talk in degree in order. Third, second, first, nothing. So they're in order, so we're good. Is everything represented? Meaning, is everything written in there? I have an x to the third, I have x squared, I have an x to the first, and I have just a number, so we're good. So that means I can just write this out with these coefficients. And then I can do this division. Pull the first number down, multiply, it's -1, add. Make sure you take your time with this. I tend to rush through it, but you got to remember I've done this a whole lot longer than you guys have, because it's real easy to suddenly multiply those instead of adding them or do some subtraction. So just kind of say it out loud in your head. Multiply, add, because you're losing all the context of the problem. It's real easy to confuse yourself. So this is 0, which gives you 0 here, which means this is -9. This is +9. There's my remainder of 0. So is this a factor? It's a factor. Meaning, when we write our answer, this is x, well, let's put them under here. X to the 0, x first, x squared. So this is just x squared -9, right? But if we think back to our factoring idea, that means that the big polynomial equals x squared -9 times x plus 1. And I'm now down to, hey, I found a factor of that thing. Only thing I have left to factor to completely factor that polynomial is that quadratic, which I can do and I can work down. It's all about whittling these things down to quadratics again so we can factor them easily. Let's try our division with this last one. So let's check our polynomial before we write anything down. It's in order. We're talking degrees here. X to the third, x squared, x to the first, and then just a number. And they're all represented. This is my x minus a, so this means my a is +4 here. This is also an activity when we do the synthetic division that I like writing the positives in front of positives in front of some of these numbers that are positive so I don't forget. So this is +4 times 1, -2, -22, and +40. Multiply by 1. 1 times 4 is 4. So this is +2. Gives me 8. -14. That's 56. And it's negative. Is this a factor? No, because this is our remainder down here. So this is not a factor, but we still need to write the answer here. So the answer from this division, x to the 0, x to the first, x squared. So we're going to get 1x squared plus 2x minus 14. Now we need to do that remainder as a fraction. So whatever's left here is the remainder. So this number goes on top. And what we divided by goes on the bottom as the denominator. So that's going to be the x minus 4. The only thing that you would probably do to clean this up is, since you've got a negative here, you would probably not see this as a plus anymore. You would probably see it as a negative. That negative would come down and make this fraction a minus. But I think, you know, plus a minus is going to give you a minus. You could probably match that answer. If it was something you were to write and you wrote plus a negative on top of the fraction, I would never mark it wrong myself. But expect that, you know, simplification, especially multiple choice type of problems that you might encounter, they may simplify it. You may need to do that in your head.